At first glance, the image looks like a beautiful patch of space filled with glowing stars and distant galaxies. But this is far more than a simple photograph. It is one of the very first deep views captured by the Vera C. Rubin Observatory, a machine designed to completely transform the way humanity studies the universe. What makes this observatory so extraordinary is not just image quality. It is scale, speed, and persistence. Its enormous 3,200 megapixel camera, one of the most powerful astronomical imaging systems ever created, can capture an astonishing amount of detail in a single exposure. A full-resolution image is so massive that hundreds of Ultra HD displays would be needed just to show it at native size. But the real breakthrough is not one spectacular picture. The observatory was built to repeatedly scan the night sky over many years, creating an evolving record of cosmic change. Instead of giving astronomers isolated snapshots, it will reveal the universe as an active, shifting environment filled with motion, collisions, explosions, and transformation. One of its first composite images already demonstrated that power. What initially appeared to be a dense star field turned out to contain nearly 10 million galaxies spread across an immense region of space. Some are elegant spirals glowing with newborn blue stars. Others are ancient elliptical galaxies radiating soft yellow and red light from older stellar populations. In the same frame are distorted galaxies being torn apart by gravity during slow-motion mergers that unfold across millions of years. Scattered in the foreground are stars from the Milky Way, their bright diffraction spikes created by the telescope's optical structure. Behind them lie galaxies billions of light-years away, layered together into a single breathtaking cross-section of the cosmos. What makes the achievement even more impressive is how quickly the observatory assembled the image. The final mosaic was created using more than 1,000 exposures gathered across only several nights. Older telescopes would require enormous amounts of observing time to produce something similar over such a vast field. One especially remarkable region captured during these early observations includes part of the Virgo cluster, the nearest major galaxy cluster to our own. Within that enormous scene, astronomers could see galaxies at completely different stages of evolution. Some are still actively producing stars, glowing with bright blue spiral arms. Others are ancient systems dominated by older stars and little remaining star formation. Among them is Messier 49, a massive elliptical galaxy filled with ancient stars, alongside NGC 4535, a striking face-on spiral galaxy rich in stellar nurseries. Far beyond them are faint reddish galaxies so distant they appear only as tiny glowing embers against the darkness. The observatory also captured dramatic evidence of galactic collisions. In one region, 3 galaxies are locked in a gravitational interaction, stretching and distorting each other into long tidal tails and luminous arcs. These scenes reveal that the universe is not calm or static, but constantly reshaped by cosmic violence operating over immense timescales. Even while observing distant galaxies, the telescope was simultaneously detecting activity much closer to home. Asteroids from our own solar system streaked across the exposures as thin lines of light. Rather than treating them as unwanted artifacts, the observatory's software automatically identifies and tracks them. This capability may completely revolutionize asteroid discovery. During only about 10 hours of observations, the system identified nearly 2,100 previously unknown asteroids. That is an extraordinary pace compared with traditional surveys. Over the coming years, astronomers expect the observatory to increase the known asteroid population dramatically, potentially cataloging millions of objects throughout the solar system. Many people naturally compare this observatory to the Hubble Space Telescope and the James Webb Space Telescope. But the Rubin Observatory was built for a fundamentally different purpose. Hubble and Webb specialize in deeply studying specific targets with incredible sensitivity and precision. Rubin's mission is to repeatedly map the entire visible sky, turning astronomy from static photography into something closer to a continuously updated movie. Its survey strategy relies on a technique called difference imaging. By comparing new images with older observations pixel by pixel, the system can instantly detect anything that changes. A supernova appearing in a distant galaxy. A star suddenly brightening. An asteroid shifting position. A black hole flare erupting from a galactic core. The observatory is expected to detect millions of changing objects every single night. The data volume alone is staggering. Rubin will generate roughly 20 terabytes of raw data every night during its decade-long mission. Over time, this will grow into one of the largest astronomical datasets ever assembled, fundamentally changing how scientists study the cosmos. The observatory has also turned its gaze towards stellar nurseries inside our galaxy. Early observations of the Lagoon Nebula and the Trifid Nebula revealed enormous clouds of gas and dust where new stars are actively forming. Instead of isolating these nebulae as decorative objects, Rubin places them within their wider galactic environment, showing how interconnected and dynamic these star-forming regions truly are. Over time, repeated observations will allow astronomers to monitor how such regions evolve, how variable stars flicker, and how stellar environments change. The observatory is not merely photographing star birth. It is documenting the process as it unfolds. That may be the deepest reason these first images feel so significant. They are not simply beautiful. They represent a shift in how humanity observes the universe itself. Astronomy is moving from isolated moments toward continuous monitoring of a restless and changing cosmos. The Vera C. Rubin Observatory is not just looking at the universe. It is watching the universe happen. What makes this moment even more astonishing is that these first images are only the beginning. The observatory has not yet entered its full scientific rhythm. Right now, astronomers are essentially watching a machine wake up. And even in these earliest tests, it is already producing views of the cosmos so immense and information-rich that many scientists believe astronomy is entering one of its biggest transitions since the invention of the telescope itself. For centuries, human beings observed the night sky as something mostly permanent. Stars appeared fixed. Constellations looked eternal. Even after powerful telescopes revealed galaxies, nebulae, and black holes, the universe still often felt static because observations were separated by long gaps in time. Rubin changes that entirely. Its mission is built around repetition. Night after night, year after year, the observatory will return to the same regions of the sky again and again. Every pass adds another layer to an enormous evolving archive. Slowly, the stillness disappears. The sky begins to move. Tiny asteroids drift between stars. Distant supernovae suddenly ignite in galaxies that previously looked calm. Variable stars pulse brighter and dimmer like cosmic heartbeats. Black holes flare as matter falls into them. Entire galaxies subtly shift through gravitational interactions. Events that once appeared rare or accidental begin emerging as part of a constantly changing cosmic system. This is why many astronomers describe Rubin less as a traditional observatory and more as a real-time monitoring network for the universe. And the scale of that monitoring is almost difficult to comprehend. Every few nights, Rubin will effectively remap the visible southern sky. Over a decade, it will build an enormous time-lapse record containing tens of billions of celestial objects and countless transient events. Some of those discoveries are predictable. Scientists fully expect Rubin to uncover millions of previously unknown asteroids, comets, and distant icy bodies in the outer solar system. It may even detect entirely new classes of transient phenomena that older surveys simply missed because they changed too quickly or appeared too faintly. Other discoveries may be impossible to anticipate. That has happened many times in the history of astronomy. Whenever humanity builds a new instrument capable of seeing the universe in a fundamentally different way, unexpected phenomena almost always appear. Pulsars, quasars, gamma-ray bursts, and dark energy were all surprises. Rubin's ability to repeatedly observe enormous portions of the sky with unprecedented depth creates ideal conditions for finding things nobody has imagined yet. One of the observatory's major goals involves one of the biggest mysteries in modern science: dark matter. Astronomers cannot see dark matter directly, but they can observe how its gravity bends light and influences galaxy motion. Rubin's vast surveys will allow researchers to map those subtle distortions across enormous regions of space with extraordinary precision. In effect, the observatory may help build one of the clearest large-scale maps ever created of the invisible structure underlying the universe. It will also contribute to the study of dark energy, the mysterious force driving the accelerating expansion of the cosmos. By tracking the distribution and evolution of galaxies over time, scientists hope Rubin's data will help refine our understanding of how the universe itself evolves on the largest scales imaginable. Yet despite all the advanced physics and staggering data volumes, part of Rubin's power comes from something surprisingly human. Its images restore a sense of scale and motion that can easily get lost in modern astronomy. When people see one of Rubin's galaxy fields, they are not looking at a handful of isolated objects. They are seeing millions of entire galaxies gathered together in one frame. Each contains billions of stars. Around many of those stars are planets. Around some of those planets, perhaps oceans, atmospheres, or even life. And Rubin captures all of them woven together into one enormous cosmic landscape. That perspective changes how space feels. The universe stops resembling a sparse collection of distant points and starts feeling crowded, interconnected, and alive with activity. Even the observatory's location contributes to the sense of significance surrounding it. High in the mountains of Chile, under some of the clearest skies on Earth, the facility was carefully positioned to maximize uninterrupted observations of the southern heavens. Every clear night, its giant mirror and colossal camera will quietly continue recording the changing sky in extraordinary detail.